Good afternoon, everyone.
I know you.
It's my pleasure to introduce to you the CAM speaker for today. Steve, we've been saving the seats for you up here. Jamol Pender is an assistant professor in the OR and IE department. This is his second year as an assistant professor. And I thought I would introduce him by telling you some of his educational background. He has gone to a number of different institutions. Each one is part of the Ivy League. He started at Penn, where he got his bachelor's degree. And then he got his doctorate at Princeton. And then did a postdoc at Columbia. It's a connect the dots of the schools in the Northeast. And you can see that it's joint work with me and Elizabeth. And I have to tell you that, honestly, I really could not spell Q before I met him.
Thank you, Richard, for the introduction. So I wasn't sure, so any questions are immediately going to be deflected to Richard or Elizabeth, so please get ready. But I wasn't sure how many of you actually knew what a queue is, and so even though you probably all experienced it. So in the beginning of the talk, we're going to do a little bit of an introduction to what queuing theory is, just to give at least some of the undergraduates and grad students a flavor of what queuing theory is. And like Richard said, this is joint work with Richard and Elizabeth. All right, so a queue basically is just a line, and often people wait in lines, and occasionally they're waiting in line for something. So in this case, this picture here it's a picture taken in Chicago during the Great Depression, where they were giving out free coffee and donuts. Actually, Al Capone was giving out free coffee and donuts. What a nice gentleman. And here you have a Whole Foods queue. They don't want you to queue in the street. And Whole Foods is very interesting. They actually have a wide variety of different types of queues that they have in their stores. So if you go to the one on Columbus Circle on 59th Street, they used to have a really long line, and then they realized lots of people left. So they sort of switched up the line to have sort of multiple lines. Even though you wait about the same amount of time, you feel like the line is shorter. So a little bit of psychology there. And this last picture actually is a place that I used to go to as a high school student. It may be a little fuzzy, but this place is actually in New York. It's called the New Yorican. Has anybody ever been there or heard of it? No? Anyway, so there's this place called the New Yorican, and they actually do like slam poetry. So a combination of poetry and sort of hip hop. And I have a very good friend who's done his poetry in front of the president and so on and so forth, and we used to hang out there. Can anyone think about the difference between this queue and Whole Foods and maybe this kind of queue, or even that one? What might be some differences between the two? Well, you don't actually see a line here. But yeah.
Imagine at Whole Foods people go in and go out when they're done, whereas at the poetry slam people try to get in and at some point it's full, and the dynamics are a bit different there.
So that's one reason. Any other reasons why they may be a little bit different? Yeah.
People adjacent to each other in the line on the bottom probably know each other. There might be small groups of people who are related to each other, whereas the people in Whole Foods are probably complete strangers.
That's another good point. Yeah.
So working back from the title of the talk, right? So the information of how many donuts are there, presumably Al Capone is not going to leave anyone without donuts. How many seats are still available in the club is not clear until you get closer in line.
Yeah, well, it's not even clear unless you're inside, right? So you don't really know that kind of information. But there's one thing that makes these queues a little bit different, and that's here, and my grad student who works on this isn't here, but this is a little bit different. So this, you're actually willing to line up outside of the club. You're not necessarily willing to line up here. This is a notion of quality. While many people go to Whole Foods because you think it's better than some other grocery store, but I think Wegmans is a little better. This is a notion of quality, and to an extent, so is this. So there's a interesting book written in Russian that talks about the queue, actually, and people would join longer lines because that line meant that it had something better to give you. So if you had a line of diamonds and a line of dirt, nobody's gonna pretty much take the line of dirt. So they're gonna go and try to get into the line of diamonds. So these are a little bit different, and I just want you guys to think about queues are different based on whether they offer something that's really in terms of quality, or you're just going to get milk, or you're going to get bread. And so lining up plays, or this notion of quality sort of plays an important role in understanding how these two queues the dynamics might be a bit different. So people are a little bit more patient to line up here as opposed to in the whole set. So my particular research actually falls into this sort of overarching theme of non-stationary queues. And what non-stationary means, all it means, at least to me, is that I'm really concerned about time-varying arrivals or time-varying rates. So often, much of the literature, anyone who takes 6500, they will learn about things that aren't time-varying. You want to learn about steady states. You want to learn about things that are constant over time. I'm more so concerned about things that vary over time. And these are sort of some of the methods that I actually use to analyze some of these sort of queuing systems, and these are just some applications that some of my work is applied to. In the Whole Foods case, when people leave, we have abandonment, which is the case where people are sort of impatient and they decide to leave the queue. That being said, I'm going to explain to you in a picture why time-varying behavior is important and why you can't really capture certain types of phenomenon just by using constant rate sort of models. So in this picture, green is going to be good and red is going to be not so good. And we're going to assume that mu is equal to 1. This is going to represent the rate at which jobs are entering the economy. So that's a fixed rate. Jobs are entering our economy. They're going to enter at a rate mu1. And what we're going to let vary is jobs sort of disappearing in our economy. That's going to be lambda of t. And so typically what you can observe is that, well, if there's lots of jobs available and jobs are entering at a higher rate, this is known as a good time. This is the great period of people are having a good time. They have lots of money. They have a job. But occasionally we go into times like in 2008. We have a recession. So jobs have left the economy. And it's important to note what society considers as a recovery is exactly this point here. So the number of jobs flowing out is equal to the number of jobs going in. But if you're a person that lost their job, you're not necessarily concerned with that point. The point that you're concerned with may be this point here. So this is the point where all of the mass here wipes out all of the mass here. And this means that if you were the last person to lose your job and you're the last person to get a job, you might get one here. And that's where you actually feel the recovery. So there's this notion of when something happens. So this is our economic recovery. This is what the government defines as us recovering. But then as a person in the economy, I only feel the recovery at this particular time. Yeah.
So your lambda now is piecewise constant, if it's red or green, or
I'm just pretending that it's a smooth curve and I didn't fill in the whole thing. I didn't bother to fill it in.
okay. But it's not. It's not actually that like your results use like approximation via like close to.
No.
Okay. I realize that you haven't shown us any results.
That's okay. So I just want to get the point out that using a constant rate model, we will never be able to explain this kind of phenomenon. So we couldn't see that we'll have a situation where we have a recession. You can actually have that this is when the government says this is the recession is over. But from the perspective of a human who lost their job, you only feel like you've recovered when you got your job back. And so this is the kind of behavior you can see with time variant Q. And that's the challenging part. Typically this is a discontinuity at that point. And if you ever drive, you're driving down the road, you get stuck in traffic, you can think of that point as like the point exactly when you're starting to drive off. You've gotten out of the traffic jam and you're starting to drive off and you're speeding up. And I think they call that a shock wave. That's when you start driving off. So I'm going to talk about dynamical systems, but I sort of want to explain why they're relevant in terms of queuing. So I often get the question, well, queues model discrete people, and people are just discrete, so why are you using these dynamical systems to actually study queuing systems? And so for the next couple of minutes, I'll explain why we might want to use a dynamical system as a way to study queuing systems. So here's actually a plot. And so here on this left here, this pi symbol is going to be a Poisson process. And the point of this graph is to show you that as I scale up this Poisson process by a rate eta and I divide by a rate eta, as you can see, as I scale up the rate, this line or this plot here actually starts looking more and more deterministic. It starts converging to the value t. So I started with something random, and now I'm starting to scale up this random process by eta, and I'm dividing by eta, and eventually I'm going to get something that looks more and more like a deterministic system. So this idea is not necessarily new. This is basically the law of large numbers. So I can think of if I set eta to 1,000, Poisson process, I can actually, they have independent increments, so I can split them up into different random variables, or eta random variables of time 0 to t, and I'm adding them up, I'm dividing by the number of them, and eventually I get something that's deterministic. So we have this for just a typical sample path for a Poisson process. So we can actually apply this kind of scaling to a queuing system, and in this case we have the infinite server queuing system. And in this case we have a system where the arrival rate is lambda of s, and this pi represents a Poisson process for the arrival, so people are arriving according to a non-homogeneous Poisson process. And this pi d is the number of departures, and the number of departures in the infinite server queue is proportional to the service rate, which is mu, and lambda is our arrival rate, times the number of people that are in the system. So if there are more people in the system, more people are being processed, and the rate at which they're being processed is much quicker. So one thing we can do to do that sort of scaling we saw before is we might scale our arrival rate, and I'm going to, for the time being, I'm not actually going to scale the service rate. One, that's actually sort of exogenous to the system. So scaling the arrival rate means that more and more people are coming to my system. So that's kind of natural if you have lots of cars on the road. So if you're modeling transportation network, you have lots of cars on the road. If you have a call center and it's around Christmas, you're getting lots of calls. So scaling up the arrival is pretty natural, but scaling the service rate is not so natural because the service rate is intrinsic to a particular customer. So your service rate is not going to change. If you're calling about, something is broken, that service rate is not going to change. The time it takes for them to answer your call is not going to change. But I should mention that the queue length is going to be somewhat inflated. So that's how we can think about scaling our infinite server queue. And if we divide by eta again, we get that divided by that. And it turns out that if you actually divide this by eta and multiply by eta, this thing stays the same. So we do kind of have a representation of the queue length in terms of a scale process. But what we can show is that this limit actually converges to a dynamical system. And this is just a linear ordinary differential equation where the arrival rate can depend on time. And we explicitly know how to solve this fairly well. And this is called a fluid limit. And so this is why dynamical systems are a little bit important. Yeah?
So if I could ask a naive question, I'm lost with terminology and I don't
Okay.
know queuing theory. So Q of t is the number of people in the queue.
Yes.
Lambda of t is the instantaneous rate of arrival.
Yes.
And the mechanism of departure, they're departing because they've been serviced or because they lost patience? Which one
They
is
are
it?
being, so this is an infinite server queue, so they are being processed because they got serviced. So as soon as you come in, the infinite server queue is sort of very special. As soon as you come in, you get service. You don't even wait.
I see.
This is the simplest sort of queue that we can have. So you come in, you immediately start getting service. Think of yourself as a VIP customer. So this was to show that basically, if we scale our systems in the right way, where we think of systems at a large scale, we can have dynamical systems or differential equations show up. Any questions so far?
Can you say again, what did you say was the infinite server queue limit? Was it that you said you're served
So-
right away?
Yeah, so, well, that's not the limit, but
No.
the limit is the differential equation.
Yeah.
So the limit of this queuing process with this eta going to infinity is, the solution to that is this differential equation.
Uh-huh.
So that's the object that we converge to. But in the infinite server queue, it's designed so that when you come in, you're processed immediately. It's not like the one that when you go to the bank, you're waiting for a teller. Just imagine there's an infinite number of tellers. You can always get one.
So that's what the infinite
Yes, sir.
refers to,
Yeah.
is the number of tellers?
Yes.
Okay, thank you. Oh, I see, infinite servers, that's
Yeah.
the point.
Yeah.
Okay, all right. I don't also do queuing right now.
That's how I'm going through
All
it.
right, thank you. We appreciate it.
So this is just a picture view of what's going on. So you have, this is our sort of original system. We scale it up, and eventually, the reason why we call it fluid, it starts, these particles get smaller and smaller, and this eventually looks like fluid. So that's sort of the terminology of how we get to this particular system. Occasionally you have, leaks, or these are called impatient customers, but we won't necessarily talk about those today. All right, so I'm going to give some motivating applications on why what Richard and Elizabeth and I have done is actually important, and how we see this in sort of in real sort of application. So this is the first picture, and this is JFK Medical Center. They have lots of these medical centers across the country, and I just want to bring your attention to 2 points. So I took a snapshot of this on my computer. That was at 4:04, and it currently says that the emergency room wait is about 12 minutes, and it is as of 3:44. So 2 things here. They're telling us some information. They're telling us that the wait is 12 minutes. In reality, it's probably not. But they're telling us it's 12 minutes as of 3:44. So there's some delay in how the information is being given to us. Now, if they don't tell us this, which a lot of companies don't do, or they actually do, then there is a delay in the information that they're giving you. And so this was really the motivating application in trying to understand how these delays, in this case maybe it's 20 minutes, actually affect the queuing system. And so if you go to Texas, actually, you'll see lots of medical centers that have this kind of technology, and they actually have them on poster boards. And so they're trying to convince you that you should go to their hospital versus a different hospital so they can make money. And so this is really the motivating application. We wanted to understand, well, how do these delays, in this case it's 20 minutes, how do these delays actually affect the behavior of the system? Another application is Disneyland. I love going here. I probably go about once a year. And so they give you a whole line of all their rides, and they tell you what the waiting time of each ride is currently, whatever that means. So they tell you some notion of how long you're going to wait, and occasionally they can take into account your GPS signal and figure out where you are in the park, and they'll tell you how far away they think you are from each ride. So at this point, I have a choice. So I really like a particular ride. I have a choice of which ride I want to go to. Now, I might choose to go to this ride. I don't know if anyone's ever gone on this ride, but it's not cool. So that's probably why it's 5 minutes, but I do have a choice on which ride should I go to. Sometimes a delay is not necessarily in the information, so this can actually be completely accurate. But the delay actually occurs because I'm a little bit further away. So suppose I have two options. Let's say I want to go to Winnie the Pooh, or let's say this, it's a small world. I have two options, but I'm 5 minutes away from each ride. Well, if everyone else is seeing 5 minutes, maybe they're also going there too, and so by the time I get there, the line is really long. So we have to think about how this delay and sort of, or distance traveled I'm making, how that actually impacts the system. Here's another example. If you ever drive to New York City, you can take the George Washington Bridge, and you have a choice. You can take the level, upper level, which all trucks are forced to take, and I put the number of miles and how many minutes it actually says, since it's a little fuzzy. Or you can take the lower level. And sometimes you have the choice. I typically like to take the upper level. I like driving with the trucks. And now you have a choice. But sometimes you have to make this choice 10 minutes before you actually are on the road. If you're a truck, you don't have to make a choice, but as a car, 10 minutes or 10 miles before, in this case 4 miles, you have to make this decision, which side am I going to take? And occasionally, even though this one says 33 minutes, it actually might take you longer because the information is not given to you in real time. Sometimes it can take you infinitely long to get over this bridge, and that's because of him. But that's okay. I think this is the last example, is, well, I'm from over here. I grew up over here, which is the Bronx, and I'm really upset that there's no Citibikes in the Bronx. And I have a choice of where should I go to pick up a bike? Well, if I'm in the Bronx, it's going to take me 10, 15 minutes to get to Manhattan. I need to choose a location because I'm going to take the subway. And so where should I pick up a bike? Well, one station might say it has 10 bikes, and another station may say it has 1. But in that 15 minutes of time that it takes me to get to the station, things could have changed. And so how do these different delays affect the system? Any questions so far?
Well, in this case, they probably should design system allow you to lock it on your iPhone, lock a bike.
That might be true, but
yeah.
I'm from the Bronx.
Yeah.
we don't have a lot of money. So I'm not a VIP Citibike customer. I can't lock it. But if I can lock it, of course, I get my bike, right? I just go to that one. But in the case I can't, then I have this decision to make. Where should I go? Things might change during the time that I'm traveling.
What are all those icons?
Those are stations. So there's lots of stations here, and then there's no stations where I.
What's the different colors, for example?
The turquoise ones are already there, the yellow ones are now there, but by the time when Jamol made the slide, they were not yet.
Yeah, so
we're
they're
growing
supposed to do expansion. They're supposed to do an expansion. So the sort of yellower ones are to come. So
What
they're
are
sort
the
of,
red?
Wait, we'll look at your iPhone for another year and then be in the promise.
What are the red symbols?
what are the red symbols?
I think at those you can buy a day pass, or at those you can buy an annual pass, which you can at every station. Something along those lines.
So there are millions of these things. I thought the red ones were the places where you get the bikes, but actually every little
Yeah, they're everywhere.
circle is a bike.
They're everywhere except for the Bronx. They're even in New Jersey. This is supposed to be New York City. Anyway, so that's my one driver's license. But, so, once again, we have this decision of where we should go. So let's kind of think of a model that can actually describe some of this behavior. So, our first model is going to be a queuing process. So we're going to have Q1 of t. I'm going to describe the second Q on the next slide, but for now we're just going to describe one queuing process. So this is our arrival process. It's going to be a unit rate Poisson process. Here we have our arrival rate lambda, and this time we're integrating over e to the minus Q1 s minus delta. And we're dividing by e to the minus Q1 plus e to the minus Q2. So for those who study multinomial logit models, this is a particular one. So think about this in the context of information. Well, I'm given information about the Q length about some time ago. I'm not given the information, well, if delta is 0, I'm given information about the current time. But if delta is not 0, I'm given information about the system in the past. And now I have a choice whether to go to Q1 or Q2, and I choose Q1 with this particular probability. So this is a rate less, or probability less than 1, hopefully. And I get to choose which system I go to based on the Q length. So if the Q1 is relatively large compared to Q2, I don't decide to go there. This pi here now is our infinite servers. That's why I discussed. So once I get into the system and I get there, I'm processed immediately. Now, there may be lots of gripes about that, but there's someone who's working on extensions on that. So pi 1 of A is going to be our counting process for the arrivals. Pi 1D is going to be our counting process for the service departures. Lambda is our arrival rate, mu is going to be our service rate, and delta is a delay in the information that we have for our Q length. Yes?
So to understand why you have the rate depending on the integral from 0 to t of this quantity, this is like you're assuming that customers are trying to estimate what the probability is that they're going to get service faster in Q1 and Q2 and are coming at that rate, and the way they're estimating that is by taking the average over time? Or what's the interpretation of the integration?
So the idea is that when I come in, I'm given two things. I'm giving the information about Q1, and I'm giving the Q length about Q1 delta time units ago, and I'm given information about Q2, also delta time units ago.
Okay.
And now, let's say Q1 is 5, and Q2 is also 5. In this model, I'll be ambivalent. I'll choose either one or the other with probability half. But in the case that Q1 is actually larger, I don't want to go to that system. I'm not dealing with the club situation today. So I don't want to go to that system. I'm going to go to Q2, and the probability that I go to Q2 is, well,
Yeah.
1 minus this. Yeah.
I think the question relates to why are we seeing an integral inside here, as opposed to, so there's some confusion here about, there's an instantaneous decision, which is the ratio you just described, and the cumulative effect of each of those instantaneous decisions is being represented here.
Yeah, so this whole integral, the integral of the Poisson process, if suppose this was, let's say I get rid of this, and I actually put the lambda here, and I put an S in some parentheses, well, a Poisson process counts how many arrivals have occurred, and then this is the fraction of arrivals that are coming to Q1. So they come at, so this is sort of like a thinning. So this sort of thins the Poisson, but it thins it at sort of a state-dependent rate.
Maybe I could add one more thought to it.
Sure.
Suppose that ratio were 1. Right. Then what you've got in the integral is lambda times t. So you're looking at the Poisson process at time lambda t. You've got a certain number of arrivals that has a Poisson distribution with that at that time. But now there's some thinning that happens at time t, at any specific time t, which is that ratio. So it's slowing it down.
Thank you. Yes.
How does your decision affect the individual delay? So this model, the individual delay is not affected.
I'm not talking about individuals, I'm just talking about the system as a whole. So this is the model for Q1. So we can have a similar model for Q2, but this time we use e to the minus Q2. That's all that changes. So we have our arrivals to Q2, and we also have our departures from Q2. And their information is delayed by this delta. So question to the audience is, what is the sum of these two Qs? Or what type of Q is that?
But the sum of them,
Just an infinite server.
We have an infinite server Q. So if I add this rate and that rate, you can always add Poisson process. You can't subtract them and still get 1. So if I add this one and this one, I'm going to get 1. So I either go here or here. And so I'm going to get a rate lambda, and this 1 will integrate to t. And here, I'm going to, if I can add that and that, I'm going to get mu of Q1 plus Q2. And so in that context, I have an infinite server queuing system. So the sum of these two gives me an infinite server queuing system. But I want you guys to realize that ideally this is meant for us to basically split half of the people in Q1 and split the other half in Q2. So if Q2 gets larger than Q1, then the probability falls, and we should be going back to a situation where hopefully we get Q1 is equal to Q2. So the idea is that we want to balance the two systems together. You don't want one system to go out of whack. So instead of actually analyzing the stochastic system, what we can do is actually analyze this differential equation. So you do the same scaling that I did earlier for the infinite server system, and we get a differential equation, or two differential equations, but this time they're actually delay differential equations, and they're a little bit different because, well, the initial condition now is a function. It's no longer just a point, unless delta is 0. So we have, this is our arrival sort of process to Q1, and this is our service to Q1, this is our arrival to Q2, and this is our service to Q2. So now everything sort of boils down, can we actually analyze this system? We have some differential equations, yes?
Those exponentials look undesirable. Would the model be completely ridiculous if you just deleted all the e's? I mean, if you just had a rational function there in that first term, lambda, Q1, t delayed.
So Brianna is working on generalizing this to different functions. The E is sort of special in the sense that it comes from these things called choice models. But ideally, we can have any function as long as it is non-negative.
Yeah.
So that we still have this probabilistic
negative.
interpretation.
I see, so taking away the E would be bad, that's.
Yeah, so
I see.
we can't just put Q1. I mean,
Okay.
actually, so if you do put Q1, Q2, Q1, and Q2,
Yeah,
in that case, when Q1 gets large, it's getting even better, or it's getting even larger. So in that case, it's going to converge to 1. So that would be a situation where if the Q length got larger, this is the club, once the Q length gets large, more people are enticed to go there. So that would be a little bit of a different
idea.
situation.
okay.
Yeah.
So why am I repelled from the longer line? If we're thinking about the infinite number of servers, the length of the line does not actually influence the total amount of time I wait. So why is there a probability of my going to Q1 versus Q2?
So we're actually thinking about customers in general. Like if you were presented with 2 queues, you typically would make a decision to go to the one that is actually small. So if you're in the supermarket, if you're at Wegmans, you're most likely, unless the cash register is your friend or something like that, you're most likely going to choose the line that's actually shorter. So
But
we're
there is a correlation between the length of the line and the amount of time I wait. Is there such a correlation here? I thought that the fact that you have this mu rate there makes my wait time as a customer independent of the length of the line. Isn't this the case?
That is true, but we're basically looking at the front end. We're not necessarily, so I could generalize this and say, hey, there's some complication with the number of servers. I agree with you that like once you're in the system, like your processing time, like it didn't matter which one you actually joined as an individual, but we're trying to look at the system from a whole. Like if I'm presenting you with information, regardless of how you're actually processed, you don't know how you're processed. I get that you know if you're in a situation like the supermarket, you kind of know how long it's going to take. But in this context, we're kind of looking at the front end. We want to know what sort of decision sometimes people are going to make and how the system looks as a result of those sort of decisions.
Jamol has a question.
Yeah.
So in your scaling here, you presumably you do this of your flow limit, right?
We didn't bother to do that yet, but
I see. So this model, this is just a new mathematical model.
sure.
It may be somewhat related to the original model.
Yeah, I can actually show that this is a lower bound for the actual model, but
Well, actually, my question is, do you think that this delay should be scaled or it's fixed in your if you want to do the flow model and the flow limit? The delay
in this
is
case, I don't think it needs to be scaled. I think you can have it be
so
fixed.
as a volume.
But it depends on whether you're scaling your service as well. If you're scaling service, then you might actually want to scale this delay because then your delay is sensitive.
I'm thinking of a large volume system. Lambda, because you have infinite servers, there's no need to scale the service anything, right? You have infinite servers there, so just as the volume gets higher, volume lambda goes, scale up, and only in that setting. So is your delay, this delay information is going to be get smaller, or?
Well, the other thing is that if we're scaling up the delay, then you're also looking further and further like into the past. Right?
I'm not saying. I'm just asking questions. So I don't know. So that's just a question. I'm not suggesting any solution.
I'm afraid you're not going to finish because the question, they're wonderful questions, but maybe we should go on.
I will speed up. Sure. So we have this is our model. So here's a picture. So we're actually integrate those differential equations with lambda 10, mu's 1, and delta is 0.34. And we actually see, well, for some time, they oscillate a little bit, but eventually they go off to 5. So in this sense, they actually are balanced and they're synchronized. So they go to 5, which is, in this case, lambda over mu, if you know much about the infinite server, it's half of that. So half goes to Q1, half goes to Q2. Situation number 2, well, all we did was change delta. We no longer have this situation where they go off to 5. In fact, if you add the 2, they'll add to 10. But one Q is large and the other one is short. And so in this case, we have this asynchronous behavior, which in many cases you don't want. If you want balance, you don't want this kind of behavior. But all we did was change delta from 0.34 to 0.4. So let's do one more. This time we have lambda is 100, mu is 5. Delta is 0.02. Let's change delta a little bit again. And change it to 0.05. We see some similar behavior. So somehow when we increase this delta, we get this asynchronous behavior between the two queuing systems. So theorem 1, the critical delay that actually separates whether we get balance or imbalance is the solution to this formula. So as a function of lambda and mu, if you plug in lambda and mu, as long as lambda is greater than 2 mu, you get the value that actually separates the behavior. So here's an example curve when mu is 0.5 and mu is 1. This is exactly what the curve looks like. So over here, we have balance. Over here, we don't have balance.
What this curve says? Is that
I'll give another one, actually. So this is the same curve, but this time we have that delay differential equation. Its behavior is stable on this side, but once we cross this blue curve here, it's unstable.
is that the delta value or what? What's the cross?
Yeah, so this is delta. So D I have here is delta. So delta goes across here, and this is lambda, and I fix mu to be equal to 1. So key point is that, remember when I said lambda was equal to 10 and mu was equal to 1, we saw a difference at 0.34 and 0.4. Well, the critical value here is about 0.36. So we should see a difference in the behavior.
By stable, you mean non-oscillating?
Yes.
So,
Yeah.
In the multinomial logic, did you have like a scale parameter as well?
We did not, and that is actually, you'll see my last slide, that's an open problem.
Could you repeat the question,
You
please?
know what will happen in the limit of that growing logic? So as I tend towards, so this is a noisy best response. What happens when I tend to best response?
Don't know the answer off the top of my head, but with the multinomial logic, you can actually build in preferences, and you can also sort of make things more sensitive as well. So that's sort of ongoing work. So the sketch of the proof is kind of somewhat standard. So we find our equilibrium, we linearize around it, and we sort of analyze the stability of, in this case, we have delay differential equation. So just finding the equilibrium, you set both of the left-hand side of those differential equations, the time derivative equal to 0, which in this case, this is what they're given. And if you do enough math or thinking, you'll figure out that the equilibrium should be exactly what the infinite server is divided by 2. After doing that, we linearize around it, which means that we basically set Q1 and Q2 to those equilibrium values, plus a little bit of a perturbation. We linearize and we do some manipulation. Hidden in this green arrow is lots of transformations that we apply. But we eventually get 2 delay differential equations. One of them is actually an ODE. And in that case, V1 is actually stable. So regardless, as long as mu is positive, which it is in our queuing system, we have stability for V1. And so now it remains to analyze the stability for V2. But V2 is a linear delay differential equation, so we're going to make this ansatz that V2 is e to the RT and plug that in. We get this equation here, which I'm going to write on the next slide, in terms of R. Now, this is sort of a transcendental equation. It has an infinite number of complex roots. You can analyze this using the Lambert W function. We don't necessarily do that in our work, but we set R equal to I omega because that's the critical value where this bifurcation happens. And we solve for the real and the imaginary parts. And now our goal is to figure out exactly where a value for delta. So if we do that, we finally get this formula, and how we get that is that we take the arc cosine of this term. So you put the mu over there, divide by, or multiply by -2 lambda, 2 over lambda. You take the inverse cosine. You need to figure out what omega is. And to figure out what omega is, you square this term, you square that term, and this squared and that squared equals 1. So you have an expression that you can get for omega, you plug that in, and eventually that's your formula for the delay. So there's another model that we analyzed. So that was a constant delay. We also analyzed a moving average model. And this moving average model was also motivated from healthcare because they give you the average wait time in the past 4 hours. So they basically integrate the past waiting time in the past 4 hours, and they post that as their wait time. So we were motivated by this to do the moving average model. So in that case, we have these differential equations. I skipped the stochastic process part. And now we have an integral in this exponential. And this is just moving over the window of t between t minus delta and t, and we divide by 1 over delta because that's the time interval. And now we sort of analyze sort of this similar model, but this time we have a moving average instead of a constant delay model. So what should we do about the integral? So I'm going to set it, so mi of t is going to be this integral 1 over delta from t to t minus delta, integral of this q length. What should we do about this integral? Any thoughts? This is your time to shine.
Leibniz rule?
No.
Oh.
No, but there's an answer.
Any thoughts? Yeah.
If you're looking for a constant limit, then that will just be replaced by the constant.
In steady state, that's true. But we sort of want to analyze these differential equations. And
So imagine you're Newton.
huh?
Imagine you're Isaac Newton and
So the key to analyzing this integral is to actually take the derivative. And why is that? Well, it turns out if you take the derivative of this integral, you actually get a linear delay differential equation. So the moving average time derivative is a delay differential equation. And so now instead of having 2 delay differential equations, we now have 4. and it remains for us to analyze this system.
Yeah, you have to do it.
So moving averages are no different than really sort of linear delay differential equation. So now we have to analyze this system. So let's look at it. Well, it's kind of crazy to see. So we have Q1, Q2, this is the moving average in green, and in magenta we have the moving average of Q2. They're all moving around. In this case we have lambda's 20, mu's 1, and delta's 0.6, but eventually they are converging. And they're going to exactly half of lambda in this sense, which is 10. Here's another system where we change the delta from 0.1 to, or 0.6 to 1, and this time they're also oscillating. So like we saw before, we increase this delta, we actually see these oscillations between the Q length. It's also important to note that the moving average is always smaller than the actual Q length, at least the amplitude. We haven't figured it out yet, but we're using Lindstedt's method to figure out what the amplitude is for this particular system. And here's what it looks like a little bit clearer for the moving average and the Q lengths. So same question arises. How do we figure out this sort of curve that divides our stable region versus our unstable region?
So physically, why did the phases change then between those? Because I was struck by the phases staying constant in the previous one, not this one, but one before it. It looks like the phase, everything's in phase, and then all of a sudden everything.
It's not. So I can tell you that like the peak here is not the peak here. It's just the spacing.
Okay.
So that's why I blew it up a little bit. So they're not in phase.
But the two moving averages are in anti-phase with each other, aren't they?
Yes.
Yeah.
And that follows because these things are also in
Right.
anti-phase from each other. So same question. Well, we have now a new stability region where it's stable here, unstable here. And remember I said, well, we use 0.6 and we use 1 as our delay values. And we found that in this region about 0.65 is where the cutoff occurs. So theorem 2, the critical delay value is the solution of this. In the interest of time and the fact that I did not put it on this slide, the proof is kind of similar. It's a little bit different, partially because actually in this setting, the curve here actually isn't monotonic, the decreasing. So it actually goes up a little bit. So there are a little bit of challenges. I didn't show it moving up, but there are a little bit of challenges that occur with this moving average model that don't necessarily occur with the constant delay. Let's talk about a generalization. So a generalization of our model is the following. Well, I'm just going to consider this mi, but this time I'm going to weight it with some function w. So this is ws, it will depend on delta. And so how does this generalization fit into the models that we've actually analyzed? And I want you to note that this goes from t to minus infinity, and that's actually crucial. So how does this fit with our own models? Well, the constant delay model we just analyzed is w is equal to delta. That's a delta function evaluated at t minus delta. Yes?
So, as you, the moving average part, as you keep on increasing delta, you always get an oscillation. So you never, so one would think as the average grows large, you have like a law of large numbers kicking and people are just randomly splitting.
Say that again?
So if I just give you no information and did random splitting, you wouldn't get the oscillation. It's kind of interesting that as your window is increasing, you're not getting
So be careful in the moving average model. If I do increase delta, I can show you an example. If I continue to increase delta, sometimes I can go from stable to unstable, and then I can go back to stable again.
That makes sense.
So that's why I said it wasn't monotonically decreasing.
Got it.
So in that case, there's some
Yeah,
complications that
because
occur.
If delta is infinite, you have to be stable.
So, so we can reconstruct our constant delay using this weighted average approach. We can also reconstruct the moving average just using an indicator function that we're in this interval, and we multiply by 1 over delta. And one of the undergraduates in the room is working on this as an exponential. Now, the beautiful thing about the exponential is that we don't have to worry about stability. So we were concerned about, well, giving people information about a system via this moving average or constant delay setting. But if we weight the information that we give them by this exponential, you always get a stable system.
When you say exponential, do you mean like this, or do you mean 1/2
I
and then
mean
0?
this is the function.
But so really this is like that, it's just a one-sided thing? It's not
So we need to be sure that
Oh, I
S
see.
is not larger than T.
So, okay,
Yeah.
so you're gonna put it, oh, okay.
So I don't want S to go beyond T.
Right, so if S is on the other side of T, you kind of feel sure. No?
So if S is between T and minus infinity, I'm okay.
Uh-huh.
If this is bigger than T, that's the future.
S and T, that's the future, and I don't know that.
Since you're only integrating to T, it doesn't
Yeah,
matter
okay.
what that function does.
Uh-huh, okay.
So we always get stability in this case, and we thought that was very interesting. In fact, you don't even get delayed differential equations anymore. In fact, you get ODEs when you use this.
Uh-huh. Yeah, it's a convolution.
So one question is, we've analyzed this case, but what if we use different types of weighting functions? Can we characterize the stability of the system just in terms maybe of our function W? So open question number 1. So there are lots of open questions in this work, and we've started analyzing the time varying case, where I said that that's really important to me. I really love time varying Qs. We sort of partially have answered this when the time variation sort of bit is a little bit small relative to the constant value of our arrival rate. There's the multi-dimensional setting. We think of Disney, there's many rides. We can generalize the multinomial logit model to incorporate preferences or sensitivity to Q lengths. I already mentioned that. What about the stability for other types of weighting functions? We're also interested in the convergence of the stochastic model to the fluid limit. You can also think of a functional central limit theorem. What about the pricing of information? So suppose now I ask you to, if you want information, you have to pay me a little bit of a fee. So how valuable that information is to you, we can start thinking about questions like that in this particular model. You can also think about epidemics. So many people have studied epidemics like the SIR model with just using either no delays or sometimes they use delays. But what about if the way that people get infected in an epidemic is actually some weighted moving average? You can think about different information procedures. So I didn't mention this today, but you can talk about, well, what if Q1 gives drastically different moving average information from Q2? What if one uses 3 hours and one uses 1 hour? How would the two Qs interact given that the information that they use is different? Or the information they give you is different and they're different times? You can think about systems with blocking. So Citibike is a perfect example. I can get blocked if I go to get a bike. And there's obviously different queuing models. So you can think of a many server, a single server. How do these systems behave if we change the number of servers in the system? We can think about systems where customers are allowed to abandon, lots of different things. So this is like really an open area of research. And even from the fluid limit perspective, or the delay differential equation perspective, there are interesting questions about, in the many server case, so we have a function like this. We have Q minimum C, and this function is not differentiable. So applying the standard kind of result, we need to be able to take the derivative of the right-hand side. And so can we actually get maybe some approximations to the system when we have a multi-server system where the right-hand side is no longer differential? That's all I have.
I'd like to ask a question that I know the answer to. Are there any examples of actual oscillating lines?
Yes, so this behavior has been reported actually in hospitals. So patients or people going to hospitals will see the information. There's a couple of them, sort of empirical papers that have discussed this sort of phenomenon. A lot of hospitals use a moving average type model, as you've seen in the slides. And in that case, they've actually seen that the numbers that vary in the hospital actually are related to the information that they report, and they do sort of oscillate as a function of time. So you can sort of compare nearby hospitals. Yep.
When you have hospitals that are in the same area do different reporting, then can you still do any of this?
Well, that was one of my open questions. So even with different reporting, and sometimes they actually they contract the same company, right, to do the reporting. So if they contract the same company, then they're probably doing the same reporting. But I think we can probably analyze it when they're doing different things. I mean, we get different results, we'll probably get different stability regions, so on and so forth. But I don't think it's actually too difficult to do. Yeah.
Did you run any simulations to check if the bifurcation property holds for the stochastic system as well?
I'm working on that now. Although I don't think so. So why that's tricky actually is the scaling is important. So if I scale my system,
I think that's related to what Jim asked.
Yeah.
Do you scale your delay or not?
yeah. So if I scale a system, I think funny things can happen. Yeah. But that's also a open area. Like actually proving the results that we can converge to a fluid limit, I don't think I think I know how to do that.
Mm-hmm.
And I can also do the functional central limit theorem, but it requires a little bit more analysis.
Okay.
Any other questions?
I actually have a comment, which is that the math that's involved in OR and the math that's involved in, let's say, nonlinear dynamics are both extensive and complicated parts of the total picture of mathematics. And there's very often there's little overlap in them. It's as if the freshman math course, calculus, sprouted two arms. One of them was the problem of taking a derivative of a function to find the maximum. And that led to the entire field of operations research. And the other was solving differential equations like the x dt equals the kx, and that led to nonlinear dynamics. And those two seem to have parted. So this is an example of a piece of work that that's involved in the Venn diagram of the overlap of those two fields.